If you raise a ball and throw it up with a certain velocity, then you can say that during the upward motion, your applied force on the ball has done work. And you must make this important observation that here your applied force is a non-conservative external force that transfers energy. So let us understand what kind of energy has changed as a result of the applied force and the work it does. Clearly, there is a change in the kinetic energy of the ball, and because the ball moves away from the earth, there is a change delta U in the gravitational potential energy of the ball as well, or more accurately, the ball earth system. So we can say the external force U provided does work W in C, but then there is also the conservative force of gravity acting on the ball and doing work. And therefore, we can say that the net work done or the total work done is the sum of work done by non-conservative force and the conservative force. Now, we also know that net work done brings about a change in kinetic energy of the object and is given by the work energy theorem. And also, the relationship between work done by conservative force and potential energy is WC is equal to minus delta U. Then if we substitute for WC and W net from equations 2 and 3, in equation 1, what we get is delta K is equal to WNC minus delta U, or WNC is equal to delta K plus delta U. So the work done by the external force is the sum of change in kinetic energy and potential energy. But then you see, this side is the mechanical energy of the system, or more accurately, the change in mechanical energy of the system. Therefore, we can say work done by non-conservative force is equal to the change in mechanical energy of the system. Then these two equations that are equivalent and mean the same thing are called energy statements for work done on a system by an external force. Next, we consider a situation where in addition to external force, the force of friction also appears. So let us say a constant horizontal force F pulls a block and displaces it by d meters, and in the process changes the block's velocity from v0 to v. Well, we can see that during this displacement d, a continuous kinetic frictional force Fk from the floor acts on the block. Then if we were to write Newton's second law of motion equation for the block, what we have is F minus Fk is equal to m into a. Now, since both the forces, that is the applied force and the force of friction, are constant, you can say the acceleration a is also constant. Then we can write the final velocity as v square is equal to v0 square plus 2ad. And solving for a, we get a is equal to v square minus v0 square upon 2d. And substituting the results into this equation, that is the expression for a over here, and rearranging a bit, gives us Fd is equal to half mv square minus half mv naught square plus Fk into d. But we also notice that half mv square minus half mv naught square is equal to delta k for the block. So we write this equation as Fd is equal to delta k plus Fk into d. And this term, or the product of force of friction and displacement d, is nothing but the increase in thermal energy. Then we can rewrite this equation as Fd is equal to delta K plus delta E thermal. But Fd is the work W done by the external force F, or WNC is equal to delta K plus delta E thermal. And this equation is what we call the energy statement for the work done on a system by an external force when friction is also present. So let us try to read this equation and understand what really is happening. You see, the applied force is doing positive work, supplying the energy and trying to increase the kinetic energy. But the frictional force, that is a thief, transfers part of it to thermal energy, which otherwise would have increased the kinetic energy. So you can say that the work done by the applied force goes into 1, changing the kinetic energy, and 2, into dissipated thermal energy. Well, another way of looking at this is that the final kinetic energy is equal to the initial kinetic energy plus the work done on the block, but then due to the force of friction, the final kinetic energy reduced by that amount. Now, if the block's potential energy has also changed, we can simply modify this equation to WNC is equal to delta K plus delta U plus delta E thermal. But then this is the mechanical energy of the system, so we can condense this equation into this form. That is WNC is equal to delta E mech plus delta E thermal. So by now it is quite clear that energy is transferred to or from objects or systems quite like money that can be transferred between accounts. And the statement scientists use in a more formal way to state the same thing is the law of conservation of energy, that states that the change in total energy E of a system is nothing but the magnitudes of energy that are transferred to or from the system. And the type of energy transfer we have discussed is work W done on the system by an external force. Thus, we can say that work done by an external force on the system is equal to the change in total energy of the system. That in turn could be the sum of changes in various other kinds of energies. And here, delta E mech is any change in the mechanical energy of the system, delta E thermal is any change in the thermal energy of the system, and delta E internal is a change in kind of internal energy of the system. And remember, delta E mech is nothing but delta K plus delta U. So if you want to understand this lesson better, you should visit this playlist, which has a number of videos around work, energy and power. And like always, if you like the lesson, do give a thumbs up, that'll be helpful, and I will see you in the next lesson.